All right, chapter 4, two-dimensional kinematics. So, uh, kinematics equation in 2 dimensions, they are exactly the same as 1 dimension, except there are 2 components. So basically, you have a x component along the x direction, and you have a y component along the y direction. So motion in x and y direction, they are independent, okay? Motion in the x direction does not depend on motion in the y direction, okay? That's the whole idea of breaking them apart to their components, because their components can act independently. You have a x component that is totally independent from y component, right? So kinematics equation in 2 dimension, there's no difference between 2 dimension and 1 dimension, and you can break those apart. Break them to their components along the x and along the y, and that way, x and y are independent, and you can work in each direction. So let's take a look at this example. And these are based on the previous things that we have already covered. A bicycle starts at point P. So it starts at this point right there. Okay, at point P and travels around the triangle path that takes her through point Q, so it's coming to point Q, and point R before turning back to point P. So we have a round trip. What is the magnitude of her net displacement for the entire round trip? So basically, starting from that point, coming back to Q, 400 meters down, and then 300 meters to the east, and then it goes north of the west for 500 meters. The total displacement once she get back to where she started is 0, right? Because she hasn't moved. So I like that. And another question that we have is, if she starts from point P, travels around, going to point Q, and then point R, and then returning back to point P, how far does she travel for the entire round trip? So basically, we have to add everything up, right? So the total travel length is 300 plus 400 plus 500, okay, which is 1,200 meters. So I like that. So equations for kinematics with the constant accelerations, if you remember them, it doesn't matter if it's along the x or if it's along y. The equations are the same, but if it's along y, we just give them a little bit of a subscript here, right there, of y to indicate that it is along y. If it was along x, we just put a little x down here to indicate that it's along x. Okay, so if you're dealing with both of them, you're not mistaking one from another. So that's the whole idea. So if I'm looking at this equation down here, I can identify it as it was written for direction along y, because I can see the y here. Okay, here I have x that indicates that it's along the x. So they're the same, right? For example, if you go back to the previous chapters to where I introduced these equations to you. So for example, this one we called it a time independent. If you don't know the time of the motion, you can use this equation for time independent formula. So these are the equations for kinematics with constant accelerations, both along x and along y direction. They're the same, as you can see. Now, constant velocity. We also have a motion with a constant velocity, right? So for our equations of motion, we would use the equation that only has one velocity, or initial velocity, or final velocity. Okay, So the term of acceleration is 0. So this term is 0 because a is 0. There is no acceleration involved in a constant velocity. This is the exact same thing that's introduced in the book, v equals vt. Okay, so remember that we had two types of motion. Okay, with constant v and constant a. Constant v was constant, so v does not change at all, meaning that v initial and v final are the same. Okay. X is vt plus x0, or in other words, I can write it like that. Delta x is vt. And notice that we have the xt figure was a line, straight line, vertical. The vt figure was just a vertical line with no slope because the velocity by time does not change. The velocity over time will stay the same. And a t figure is always 0 at 0. So velocity is constant. Acceleration is 0. On the other hand, we have a constant acceleration motion. For those with a constant acceleration motion, it is important to identify those. And we're not dealing with a variable acceleration. We're always dealing, of course, with constant accelerations, meaning that v is changing, but the rate of the change is the same, and that's the acceleration. That's what the acceleration is. So v is at plus v naught. V bar is delta x, delta t, delta t. Delta x is half a t squared plus v0, initial velocity, vt times t, right? Time-independent equation, v squared minus v0 squared equals 2a delta x. What else did we have? Here's a list of them. We have it right there. The constant acceleration. Okay. So if I want to draw xt figure, it will be something like this. Right? Either something like this or something like that. Okay, because it is to the power of 2, t is to the power of 2, so you're not dealing with the linear anymore. Okay. Now, if you want to draw vt, then this is a linear. V is changing over time. And the slope is just acceleration. So either this, or something like that. So this is for velocity of positive, so velocity of negative. Right? And if you want to show the acceleration, not velocity anymore, acceleration. Want to show the acceleration, then acceleration is always constant, either positive or negative. So negative. But it's constant over time, it does not change over time. So these are the formulas that we're dealing with here. So the constant velocity or constant acceleration. Right? Projectile motion, or motion in two dimensions along both x and y. It's very important. You will have this in the test, so make sure to understand it very, very quickly. Projectile is any body given an initial velocity that then follows a path determined by the effect of gravity and air resistance. Okay, now I would like to get rid of this air resistance because we're not dealing with that this course. So yeah, kind of like that. So determined by effective gravity. Now, when it comes to playing with air resistance, the equations get really, really complicated, and you need to have some sort of integration based on velocity to find, for example, x or delta x and things like that, which are generally beyond the level of this course. So begin by neglecting the resistance or air resistance and the curvature and rotation of the earth and things like that. And the object is in free fall, and you know what the free fall is. Okay, you know what the free fall is. Acceleration has one component, ay, which is always negative g or negative 9.81. Okay, so the opposite positive. Okay, and let's actually see if I can add a page here and talk about the free fall one more time. Or maybe I can just extend this. That's even better. So assume that you have ground. Okay. So this is ground. All right, and then you are holding a ball right there. And you are just throwing it upward, exactly vertical, okay? With a velocity of v0 initially. Right? Let me actually see if I can grab it. Oh, what did I do? Right. So just putting it down here. A little bit to give us a little bit of room. There we go. Right, so you're throwing it upward with an angle of 90 degrees with respect to ground, so kind of vertical. And so this is kind of a free fall, right? And the free fall is not necessarily meaning that you are dealing with something falling down from rest. It's not necessarily like that. Everything that is vertical, motion of the vertical, as a vertical component could be free fall, as long as it's only affected by gravity. Okay, so now this ball will go up to this point, and then we'll go up to the maximum point, and then it'll fall back down, and it'll hit the ground. Okay, so at this point, the velocity is not v0 anymore. It moves slower. Okay, so it is v1. At this point, it will stop. Maximum point. It will go all the way up and it will stop. So the velocity here is whatever it is 0, whichever way you want to show it. It's always 0. At this returning point, it has the same velocity as v1, but it is negative v1 because we have positive being up and negative being down. At this point, it has the same v0 velocity, but negative because it is downward. And at this point, it just hits the ground with kind of a velocity, but we know that velocity is zero. Remember, the meaning of negative velocity means to the negative direction. So if I have negative velocity, it means that it is in negative direction. Okay, that's what it means. So when you're looking at this, why is this happening? Why is it starting from v0 at this point, going all the way up, getting less speed, less until it just stops, and then falling down and gaining speed again? The reason is because of the gravity or acceleration, a constant acceleration downward. Okay, this guy, a of y, negative 9.81 meters per second squared. Then the g, okay, is always down, 9.81 meters per second squared. It is always down. So that's why it starts from a high velocity of v0, but this negative g is pushing it down. Okay, it's slowing it down. So it gets to v1, but with a lower speed. It gets all the way to the maximum point, but then this g has made it stop. At this point, which is the stop point, like stop here, okay, which is the stopping point, then the g is pushing it down again, and it's gaining the speed, but it's going in a negative direction. Okay, so let's actually do that. I can get rid of this positive and negative, and I can just put a arrow indicating that which direction is positive and which direction is negative. So this is the positive direction, and this is the negative direction. Okay. So this is the free fall. If the free fall is happening, then the acceleration is always the gravitational acceleration because of the gravity, which is always negative 9.81. And we always assume the up is positive, the down is negative. Since g is always down towards the ground, towards the Earth's center, it's always negative. And at that point, the maximum point, the acceleration is the same, but the velocity is 0. So it is moving up to that point, and then falling back down. Okay? So keep that in mind. The projectile motion is, and along the y direction, is always a free fall. Okay? So take a look at this. We have a x and y motion when it comes to 2 dimensions, so in projectile motion type of thing. So along the y direction, it's always a free fall. So the red ball here is freely falling, but the yellow ball is doing a projectile motion. So it means not only it's falling down, but it's also moving to the right. When you're looking at this, so each line that you see here is 1 second. So here I have starting point of t equals 0 seconds, t equals 1 second, t equals 2 seconds, t 3, 4, 5, 6, so on and so forth, right? So now when you're looking at this, they are exactly falling with the same rate. They are falling with the same rate. 1 second later, they're both at the same point along the y direction. 1 second later, they're exactly the same point along the y direction. 1 second later, they're exactly the same point along the y direction. So technically, I have my y direction here, and I have my x direction here. So in other words, I have x here, and I have y here. Right? So an object freely falling and an object doing a projectile motion, meaning not only it's falling down, but it's also moving to the right or left, they are falling with the same rate. Okay? They are both freely falling along the y direction. So they both do this along the y. All right? They are both falling down with a constant acceleration of negative g or negative 9.81 meters per second squared along the y direction. So we can analyze the projectile motion. We can analyze these balls, these yellow balls, okay? We can analyze them by analyzing the free fall. So rather than just analyzing the projectile, since they are along the y direction the same motion, I can just analyze a free fall instead of analyzing a projectile motion. Okay? So take a look at this. Condition for projectile motion. So we have a ball or an object, okay, doing a two-dimensional motion or a projectile motion. Okay, projectile means two-dimensional. Projectile motion means 2D. Okay, 2D. Two-dimension. Conditions for two-dimensional motions. So we have a box or an object or whatever at this point with an initial velocity above the ground, okay, so with an angle of theta or something, with an initial velocity of v0, going all the way to the maximum point, okay, and then falling back down to this point, okay. We can analyze this, we can break this apart in two motions. One along x and one along y. So in x direction, it is a motion of constant velocity, and in y direction, it is a free fall with a equals negative g. G is always down, right? That's our g right there. That's the g, right? So it's always down along the x direction. So in x direction, we do not have any type of acceleration. It's constant velocity. And along the y direction, it's always a free fall. Okay, there's always a free fall. Okay, so I can, if I have a projectile motion type of thing, I can just look at it and analyze it as if I'm breaking it to components along x, along y. Along x is always constant velocity, no acceleration at all. Along y, it's always a free fall. It's always a constant acceleration with the acceleration of gravity. Great. So here is a point that I would like to add a page here and talk about the projectile motion a little bit. So there are three types of projectile motions, or motion in two dimensions, as I can call them. So the first one is the type of motion that you have So let me actually write that. The first one is this. So I have a x and I have a y, but then, so that's my x, and that's my y, but then this motion starts from this point, not above the ground, with a velocity of v0 along the x direction without any theta. Okay, so in other words, theta is 0. That's the first type. Okay, so if I wanted to write it a little bit more clear, theta, or the angle, is 0 degrees. All right, that means I can extend my y direction a little bit, all right, and kind of try to project that. So it starts with a velocity, and it moves like this. All right, moves there, and there, and there. We know that this is the first type, so we know that along the x direction is always a constant velocity. So along the x direction, we always have v0, always have v0 along the x direction, all the time. But along the y direction, we have a acceleration. It's freely falling, right? So it's negative 9.81 meters per second squared. As an object is moving along the y direction, falling down, freely falling down. And it's always down, so I know that the acceleration is negative g, always down to the ground. Okay? So for example, at this point, it has some sort of a vy associated with it because it's gaining the speed as it's falling down. It's freely falling, right? So it has a component of velocity along x. It has a component of velocity along y direction. So I can just add them up using the vector addition that we learned, and I can say that this would be the velocity at that point. Okay, so in order to write down the equations, initial velocity. So the velocity of initial velocity is along the x direction is always constant, which is v0. Along the y direction, initial velocity is 0. Initially, it has no velocity along y. It's freely falling, right? So the initial velocity along y direction is 0. And along the x direction is always the same. It's always v0. It's always v0. Cool. Final velocity. So final velocity, v of x along the x direction is always constant. We know that. V of y, we have a formula for it, right? Let me scroll back up a little bit. sure what I'm talking about? Well, we have y. These are formulas for v, right? So keep that in mind. Okay, so v of y is at, but a is negative g, right? So negative gt. And then if I can find it based on, actually do that later. So negative gt is right there. And time independent formula, v squared minus v naught squared is negative 2gy. So what else did we have? So these are just velocities. What else did we have? We had, if I use this along the x is the same, doesn't matter which point, it's always along the x, it has always v0. Along the y, so I can also write it down like this. If along the y initially was 0, which is right there, so this is 0, so then I have negative 2gy here. Okay, and if this angle, if I call this angle theta, then tan of theta is vy over vx. Okay, let's talk about the x formulas. So the x formulas, x is always a motion with constant velocity along the x direction, motion with constant velocity in x direction. So I have v sub x t, or I can just write it v naught t, okay, v0 t. And y, which is free fall, so half at squared plus vt. V initially along y is 0, so negative half gt squared. So a is negative g, right? So that's why we have a negative half. Okay, this was the end of part 1. I'll continue with part 2.